Welcome to the ET380 Amplitude Modulation and Basic Transmitter Lecture video. Okay, modulation is the process of impressing intelligence upon a carrier frequency. A transmitted signal is made up of the RF carrier and unmodulated intelligence. Modulating signals can only affect three factors in the carrier frequency. Amplitude modulation affects the carrier amplitude only. Frequency modulation, FM, affects carrier frequency only. We'll study that later. Phase modulation, PM or indirect FM, affects the carrier phase only. Amplitude modulation impresses intelligence, audio messages on the carrier simple by varying the amplitude. Audio frequencies are first processed by audio frequency amplifiers, filters, and compressors. Modulator stage is an AF power amplifier with RF amplifier as the load. Okay, amplitude modulation process. Audio is superimposed on the RF carrier. So here we have our audio signal. Our carrier signal goes into the AM modulator, and our output is this modulated AM signal. The modulated signal contains original frequency, the carrier, plus the sum and difference frequencies. So here we have the lower sideband and the upper sideband, which is about 1 kilohertz. Modulation produces two sidebands when we need only one. Phase relationships must be maintained between the sidebands and the carrier. Sidebands are different frequencies than the carrier, and the phase can be shifted differently for the different frequencies. Carrier frequencies can beat together and produce interference. 10 kilohertz beat frequencies on AM band at night are common. The carrier frequency power is not needed in the receiver. Most of the power in the carrier is therefore wasted power. So here we show the carrier at 1000 watts at 100% modulation, and our lower sideband is 250 and our upper side is 250 watts. The intelligence is only in the sidebands. Transmitted signal bandwidth is twice as wide as the frequency range of the modulating audio. Our current AM applications. Amplitude modulation is primarily used in radio broadcasting, or traditional AM radio stations, citizen band radios, aircraft communication, and shortwave radio. Low-level modulation is used on low-power transmitters often. Modulation can be applied ahead of the final power amplifier, shown here, and less modulator power is required. Class A or Class B push-pull amplifiers are required in the final power amplifier. AM transmitters may use high-level or low-level modulation. High-level modulation is the most efficient for high-power transmitters. Modulation is applied to the high voltage to the power amplifier, shown here. And Class C bias is used in the final power amplifier. Voltage is modulated. Modulator power requirements are high, and we will do a Class C bias amplifier later. Here showing a simple transistor modulator showing the carrier and the modulating signal going into a transistor with a resonant circuit above it producing our carrier frequency. Here's a high-level collector modulator showing our carrier input into a transistor, our filter circuit going to our amplifier, and our modulating signal or microphone going into a high-power audio amp and going through a transformer and out. Here's a circuit of an improved transistor modulator. Here's our modulator signal going through a buffer into our transistor, our carrier frequency put in through a transformer, our filter circuit, and AM out. Okay, here's our RF oscillator and driver circuit. Here we have a ceramic oscillator producing our frequency, a transistor, a coupled output and filter. So here's a transistor input into an output. So this is generating our oscillator frequency for the modulator and our input signal. Here's a transistor AM modulator circuit, which we're going to build in the lab, where we have our input frequency, our modulating frequency, and our output through an output filter. Here's an op-amp AN modulator circuit, which we're also going to build in the lab. Shows an op-amp with our audio signal, a transistor with a pulse signal, and an output amplifier filter. Here's a basic transmitter. Transmitters produce a radio frequency carrier wave. All large stations use vacuum tubes in the power amplifier. Here's a simple unmodulated transmitter for sending Morse code. So we have the sending key, an oscillator, buffer, amplifier multiplier, driver, and our power amplifier, which goes out to an antenna. So what we show here is our modulated signal, and we have a size of a dot or size of a dash. And this signal is interpreted at the receiving signal, and you get the Morse code dot dash. Okay, basic transmitters. The carrier frequency is a high frequency RF sine wave fed to an antenna and radiated as E and H lines, which we'll cover E and H later. The carrier originates in a master oscillator, which must be very stable. Regulated voltages and temperatures are often used. Physical construction is rigid and protected. The oscillator is usually followed by a buffer stage. Oscillator is often operated at low frequency and followed by a frequency multiplier stages. Oscillator signal is amplified, then fed to a power amplifier to be radiated by the antenna. The carrier frequency is radiated from the antenna. Antenna should be resonant and matched for impedance. Modulated carrier frequency carries the intelligence, the message on it. The simplest transmitter would transmit only RF carrier. Morse code is sent by key and transmitter on and off. And the simplest form of modulation is on-off or OOK keying. Here's a block diagram of a basic AM transmitter. We have the oscillator, our buffer, RF amplifiers and drivers, our intelligence input, which is our audio, a buffer, a modulator going into and combined in our RF power amplifier and going out to an antenna.